So today we're calling the Fundamentals of PCB Design Part 1. This is going to be a two-part series. First this week, the first one happening this Thursday, and then the next one happening the following Thursday. This is ran by Dr. Shane Smith, who's to my left right here, and is a subject matter expert on printed circuit board design. And the cool thing about this is you don't need an expensive license to do this workshop. It's with a free piece of software. Closer. There it is. It's a lot louder. Thank you. So now you can hear me. So it's with a free piece of software known as Kicad that's been in development for many, many years, I think since the late 90s or something like that. But it's a very robust tool that you can get for free and do a lot of stuff for free with it. He's going to go through schematic capture, layout, DRC and Gerber generation, generating your own BOM, and even design for test and post-fabrication, kind of the whole flow of developing your own PCB and testing it and making sure that that it works. So exciting. I don't want to take any more time. I want to get this started right now. So without further ado, we have to change presentations, but I'd like to introduce Shane Smith.
Okay, everybody. Gus, thanks for the intro. My name is Shane Smith. I'm going to talk a little bit about myself after I give an overview of what I'm going to talk about tonight. It's great to see everybody here. And hopefully what I'm going to provide over the next two workshops, as we're calling them, is an intro to printed circuit board design. And the idea is not really to go super deep. It's just to kind of expose you to the concepts so that you could go off on your own and kind of figure this out. So it just gives you a starting point. And so I'm hoping to talk for roughly an hour today. And then at the end of that, do like a hands-on thing where everybody's kind of working, and I will walk through some of the processes in the schematic entry. We'll all kind of work together. So if you haven't installed Kicad, you got your laptop here, as I'm talking, maybe make sure you get it installed. And so we'll be ready sort of after the first hour to get going, okay? So as I said, next week, roughly an hour talk, then we're going to do 30 minutes hands-on. This is geared to a general audience. So, I think a lot of the folks in here, you're all like, double E majors. You've probably already done all this before. But I geared this to people that have not, okay? So this may be beneath you, but I think you'll still get something out of it. The next thing is the idea for this whole series is sort of, Gus talked about the Arduino. To me, I'm kind of a snob when it comes to electrical engineering. I design integrated circuits, which means I'm kind of on the top. At least that's how I feel about it. But this Arduino stuff is amazing. It gets you connected to the hardware really easily. So I'm a huge fan. And so in this lecture series, we're kind of talk a little bit about how could we design a board to plug into an Arduino. So the topics we're going to go through is going to take you from the very beginning, give you a little exposure about the materials of printed circuit board design, and then take you through actually designing a board. So I guess, I will take a few minutes to talk about myself. Why am I here? Why should you listen to me talk to you about this subject? I've been doing microelectronics for 25 years. I started my career in the physics department at Ohio State, where I developed electronics for high-energy physics experiment research. So there's a group of people in the physics department that they build electronics that go into the Large Hadron Collider. So that's what I did for basically half of my career. And as a part of that, I had to build a lot of custom electronics from the chip level to the board level to the system level. So right now, I am the president of Sensix, which Gus mentioned. I'm also a research scientist at Ohio State, so I'm a relatively busy guy. But my job at OSU is basically to mentor graduate students, postdocs, and there are a couple undergrads in here that work at ESL, which is across the street, that I work with, and thanks for coming. So that's me, pictures of me doing real work. Another thing about me is I said I've done a lot of stuff. I'm an IC designer. I'm familiar with doing rad-hard ASIC design. I'm familiar with making sort of product level production of rad-hard modules that have ASICs on them. in the several hundreds of units for the Large Hadron Collider that I mentioned before. I've designed a lot of boards in my day, so high speed to low speed, analog mixed signal boards. I've done a lot of ASIC testing. I've done a lot of firmware development, so that's on the FPGA side. So not only have I done chip design, but also a lot of work with FPGAs. And I spent a lot of time working in the clean room doing process development to make diamond detectors, which are also used in particle physics research. Okay, so in terms of, this is kind of an example board that I'm proud of that I made when I was in physics. It was a board to read out that telescope that you see here. It's at a place in New Mexico. It's at about 14,000 feet. But this is to take data from something called the Baryon Optic Sky Survey. So I don't really know the science, but it's like a dark energy thing. But my job as an engineer was to just make this board, hook it up to the telescope so the data could be read out. So the cute story that I have there is, we were developing prototypes. The first time I went to this thing, people warned me about altitude sickness. I'm sitting there soldering something, and I look down, and there's blood all over the table. It's because I got like a nosebleed from being at altitude. But anyway, this is something I've done in the past and gives me some street cred in terms of what we're going to talk about. All right, so we touched on this at the beginning, but if you haven't installed Kicad, now would be a perfect time to do it. We're not really going to use it yet. I don't know, Gus talked about Kicad. It is, to me, an amazing piece of software. The fact that it is open source, the fact that it is free, the capabilities that is offered, it really is comparable to something that you would pay for. And to be honest, we use it at Sensix. And we've done some relatively complex designs here, RF designs that have sort of big digital components. So stuff that's actually quite complex, we've done with Kicad, and it works really great. So I think I'm not here to sell Kicad because it's not being sold, but so Rami's pointing out that yes, we have these USB sticks with the software downloaded on it that you can use to install on your computer. Okay, so let's get going here. What is a PCB? Does anybody want to tell me what a PCB is? Go for it.
Printed circuit board?
It is a printed circuit board, but what is it? Go ahead.
It's to wire electronics without the need of wires.
Okay, that's a great explanation. So you're exactly right. So what is a PCB? It is a flat board that is made of a non-conductive material. That material can be a lot of things, which we'll kind of touch on later in the lecture. But typically, the most common is fiberglass. And then on that fiberglass is a copper sheet. That copper sheet, to become something you can actually use, the place that makes the board will do what's called etching, photolithography and etching to make the patterns that you see here. So on a PCB, you can see these holes. There are holes through the board so that you can insert components. And then there are traces running around the board to make the electrical connections. So like the gentleman over here said, there are no wires here. The wires are thin pieces of copper that are glued to that fiberglass backing. So furthermore, what is a PCB? This is something that, if you opened up a computer from the 80s, you would see something like this. But all of the traces that we saw on the previous board, now the board looks green. Can anybody tell me why that board looks green instead of copper? Go for it.
The fiberglass, it's like an artifact sort of from the chemical process to etch the board, I think.
Does anybody else want to try? Go for it.
It's a protection layer so you don't short anything out or
right.
cause interference.
So this is called solder mask. So at the end, it's a protective layer, as you said, to cover that copper because copper oxidizes really quickly. So if you left the copper exposed, it would turn green and it would be hard to solder to that. So the green stuff that you see is a protective covering for the copper. And you can see where you do solder joints. It's silver because there's solder there. There's no solder mask in the location where you would need to solder. All right. So the nice thing about PCBs is that it allows you to make something very compact, very organized, that can mechanically hold electrical components together. And, you know, this is an iPhone. Everybody's got one in their pocket. But it has some pretty complicated boards inside of it that hold chips, resistors, capacitors, voltage regulators, and so forth. Okay, so, you know, this is just kind of, you know, we're going to go into a little bit of details about designing boards and some of the considerations that you have to have. But I thought, you know, we're going to go through kind of a detailed example of something a PCB designer has to think about. So what I want us all to go through in our minds is we have this through-hole resistor on the board, and it is, I guess I can do this if I can find it, yeah. This guy is known as a through-hole resistor, okay? And I want everybody to think about if I had a 9-volt battery like this guy, and I hooked it up to flow through this trace on the board to that trace, like through the resistor to ground, what current would flow in that resistor? Okay, so it's a exam for you guys or something to think about. So first, how would you guys approach that problem? Go for it. Exactly right. So can anybody tell me the value of that resistor? That's another way to do it. But before you apply the voltage, I'd like to know the value of that resistor. Can anybody tell me the value? Go for it.
I'm going to get the power of 10 wrong. It's like 2 mega ohms or something similar. I forget which one quite would be.
Okay. We're getting,
I feel like that was 27 and then silver.
we're getting closer.
29 and silver.
Let's keep going. We got the cheat sheet here. Okay. So here's the cheat sheet. So you know, we don't really use through-hole resistors anymore unless we're doing a power device. But in order to use a through-hole resistor, there's the thing called the color code. And back in the day, you would have memorized this, and a couple of people would have known the answer, probably. But that actually is a 0.39 ohm resistor. So it's not even an ohm if you read the chart. Okay? So if you do the math, which I'm not going to ask you to do, but if you do the math, you can see at the bottom there, with that 9-volt battery, we've got 23 amps going through that resistor. So then I would ask, is that a problem? Okay. So you know, everybody's in school. This is the power equation. Again, we're not going to solve this. But that resistor, if you're running 23 amps, it's going to be 200 watts. So that's a problem. It's going to catch on fire. You know, think about what a 100-watt light bulb, how hot it would get. This thing is going to burn, okay? So how does this relate to PCBs? Okay? So this is kind of to sort of describe how you would go about solving, is that okay for the board? It's clearly not okay for the resistor, but what about the board itself? So if you're a PCB designer, there's a wealth of information available on the web, like online calculators. There are a lot of resources. And so I just stole one here from a company called 4PCB, which we're going to talk about a little bit later. But this tool allows you to calculate what is the temperature rise of a printed circuit board trace given a current and a thickness of a wire, okay? So here I've typed in 23 amps. I put the thickness of the copper. So this is a 1-ounce copper. I'm not going to talk about what 1-ounce copper means yet. I'll talk about that later. But you type this thing in, and I arbitrarily picked, let's let it go to 1,000 degrees, okay? Why 1,000 degrees? The melting point of copper, you can see here on the right, is down here. Let's see, somewhere. Yeah, the melting point of copper is 1084 C. So if you ran 23 amps, it would melt at some point, okay? So what it tells you is that you would need a trace width of 142 mils. Again, later we're going to talk about units, which are important in PCB design, but 142 mils is a lot larger than that trace, which I'm estimating on that board, if you can see over here. This guy is only 10 mils. So again, this trace is going to burn as well. Okay, so that's just one example of, if you're a PCB designer, you have to think about something called electromigration. You're going to burn up the board if you pass too much current, so you have to design the PCB traces to be wide enough to handle the current that's going to flow on your board. So anyway, just a quick example there. So in terms of the design flow of printed circuit board, how do you start and how do you get to the end? I'm just going to kind of go through that in a few slides here. So there are some fundamental things that you do along the way that I'm just going to hit on. The first is that you need to make a schematic. Okay? So a schematic is a conceptual drawing that illustrates the connection between the electrical parts on the board. So it's purely, it's not a real representation of the physical design. It is just a cartoon showing you how things are connected. So this, while it's not the physical design, it's incredibly important because you have to determine how are you going to make your connections on the board to perform whatever function it is that you want. Okay? So you have to read about the components, you have to understand their specifications, and then connect them as you see fit on the board. The next part is, once you have done the schematic, this is your electrical design that you're then going to physically implement on a PCB. You work on something called component placement. So you have all the components in the schematic. The next step is that you take them into the physical PCB and you arrange them on the physical PCB. So why is this important? Well, one, this basically determines the size of your board. If you space the components really far apart, then your board has to be big to accommodate that. If you place them too close together, this is illustrating a situation where, let's say you had a hot part, and what if this is a temperature-sensitive part? This guy's getting hot, the heat will go over to that part and maybe impact its performance. So you have to think about even thermal things when you're doing your component placement. So this is a very critical step. This is also critical because when you do the routing, that's the interconnection between the electrical components on the board. That routing is a function of where the components are placed on the board. So if you had a chip over here talking to a chip over here, it's got to go all the way across the board to touch it. Perhaps you should put them close together. Okay? So this part of the process is critically important. And in fact, I think this is where people spend a lot of their time, actually. Because if you do this right, then the actual routing is a lot easier. So, okay. So the next step is that, as I said, you're going to take your time, make your schematic. You are going to place your components on the board. The next step is to actually do the routing. So this is what we're all familiar with, making connections between chip to chip, resistor to resistor, and so forth, so that you can make the connections that you need on the board. So this is the next question that I have for the audience, is could someone tell me why some of these traces might be thicker than others? Okay, go for it.
Because it will have higher power.
That's right. That's exactly right. How about these squiggly lines? What do we think that might be? So let's pick somebody else. Go ahead with the purple shirt. Yeah.
Is that like a resistor of some kind?
It could be. Does anybody else have a guess? Go ahead.
Is it length tuning for high-frequency circuits?
Exactly right. So that's a length tuning. And Kicad allows you to do that in a very efficient way, actually. So, So how about this guy over here? What do we think these circular things are on that square, the red square? Does anybody have a guess? Philip, go ahead.
Vias?
Those are vias. Why might they be there?
Are they stitching vias
they're most likely to connect to the ground plane, but they're probably thermal vias to bring heat away from the component that would end up being there. Go ahead.
People online are just saying whenever you get a response from the audience, they'd like to hear it.
Ah.
Sorry, so I think the one with length matching.
Yes, so we had a response on length matching, which was correct. That's for the squiggly lines. We had responses on these vias here, which I did not design this board, but I think they're probably used to remove heat from the component that will eventually be mounted there. All right, so that's the routing. We're going to actively do this all together later. The next thing, which is critically important, is how do you distribute power and how do you connect the grounds? I actually think I made a mistake here. I should have probably talked about the grounding and the power first before the routing, because that's actually the process that we should flow, that we should go through. But anyway, we'll talk about this second. So I would say that 90% of the boards that are designed, the way you get performance out of them is that you do the power and ground distribution correctly. So this is where you can make or break the design, especially if it's a high-speed printed circuit board or an RF printed circuit board. I mean, you can see this image that I picked is artistic. Like, you see all these shapes weaving around on top of the dielectric material, and this is sort of the ground is around the edge, and it has these vias. I would like to ask if anybody in the audience could tell me maybe what is happening in this type of PCB. Not Josh or Dominic. Go for it, yeah?
So these vias are like stitched in a circle around this thing, which makes me think that they're probably trying to shield either what's inside of it from emissions outside of it,
Yep.
or what's outside of it from emissions inside of it.
Exactly right, yep.
Or both.
Or both. So the answer, could you repeat the answer? My brain is not the best. What you said, that it's to shield what's outside from what's inside, that
Or what's inside from outside.
or what's inside,
Shielding
yes.
something from something else across that boundary.
Exactly. That's a great, that may not be the complete answer, but for the sake of what we're talking about, that's a great answer. So how about all these cute shapes? What might be happening here? How about Dominic? I'm calling on you. What might be going on here?
Could be a matching network.
It could be, yes. So this is probably an RF circuit board. So RF is radio frequency. It's a very high operating frequency, where these components are actually resistors and capacitors, and they're impedances that RF circuit needs in order to operate properly. So they're not components. They're microstrip, engineered designs that are built directly on the board. Okay, so in this case, if this is an RF board and you didn't have this ground shield, maybe the noise from that RF circuit would couple into the other domain and completely break the board. So you have to think about that kind of stuff. Go for it.
How much, if that is a matching network, how much of that is automated by the software you use, and how much of that is you draw every single shape and put everything exactly where it's supposed to be? What's the percentage
Yeah.
between those two?
Okay, so the question from the audience was, how automated is this type of RF design? It's kind of a complicated question to answer. So it depends on, so oftentimes you can have a printed circuit board design software tool that has a library of RF components like this that are parameterizable. So you might have a shunt capacitor that you can vary the width, and but you as an engineer still have to do the simulation. The automation aspect, I've never. Mike, have you ever automatically designed an RF PCB? Right. So so there are tools to help you, but to automate, those tools aren't super mature, at least from my knowledge. Yeah. Sure. Okay. So that's grounding from an RF board perspective. But on a digital board where you have a microprocessor and you're trying to send signals from the microprocessor across the board to connectors and other parts, those connections have to have return paths for the current. So you're not just sending the current from one place to the other. That current also has to return to its source. So that is done by having a nice ground connection. And that's typically done with a ground plane, which we'll talk about next week. But the next thing is power. The chips on your board, the components on your board, they need to have a DC supply typically so that they can then do whatever operational function. So if you don't, if you supply a little tiny connection to a big chip that requires a lot of juice, that chip will be somehow, it won't receive the voltage that it needs or the current that it needs to operate. So we have to think about those kinds of things as we do our PCB design. So the final thing in the process is that you have to think about design for manufacturability. So can anybody tell me what they think design for manufacturability means? Go for it. Exactly. So the audience said that you have to design for manufacturability because you might have to do it with machines, and if the machines can't assemble it, then it can't be assembled. That's in a nutshell what the audience said, and that is correct. So not only machines, actually humans. So you could do a design in such a way that a person could not solder. Like you guys, if you actually go through the process and make a board, you could make an error that you couldn't solder a certain component because it was too close to another one. Okay? So, design for manufacturability sounds like something that happens on an assembly line, but it also applies to, your board that you may end up making at some point in your career. So, there's a big thing about this when you go back to the discussion of, having things made in a factory or an assembly line, is that there's a large body of rules, regulations, things that you can follow in order to ensure that you meet these guidelines. So this is, I don't want to say an art form, but there are people that specialize in, let's say, taking a prototype board and then reducing it to something that can be made in the millions, right, reliably. Okay, so with that, I actually have a video, which could be a bad thing because it might not work, but I think it will. But this is actually a place in Westerville, Ohio. They're called Avcom SMT. I've actually worked with them for a long time, but they're a small shop that does PCB assembly. Like that's their business. They have automated assembly machines. And they also have human beings that actually work all day long soldering, but they have machines as well. And I thought it would just be kind of cool. This video I think is cute, but it shows you kind of what it looks like when a PCB is being assembled by a machine, and it runs for a couple of minutes here. So let's see if I can get it to. You guys have already watched this, you said? Oh, okay. Oh, nice. So you can see there's, on this green, there are multiple copies of the same board, right? So it's stuffing more than one at a time.
Is this sped up at all?
No, it's real. It's crazy. Yeah, it's yeah. So what that guy did was put all the components. It's going to go into an oven now. So they do the reflow where all the components that they place get soldered in this oven.
During this process, when it first places the components on the board, are they loose or are they stuck in at least in some partial way?
Yeah, they're in what are called reels. So they're in reels or tubes. So the people who make the ICs, make the resistors, they have a packaging method that is compatible with these machines. Yeah.
Well, I'm thinking about, so they go into the oven to kind of melt the solder and make a good connection on it, right?
Mm-hmm.
But that thing moved pretty fast. So when the machine first places the component onto the board, what keeps it on?
surface tension. Like there's a solder paste. It has two balls of solder. Let's say, for example, if it's a capacitor, they go down, put the component, and the surface tension of the solder paste is enough to hold it. Because the capacitor weighs nothing. What is this? Oh, they have a 3D printer, which we all have 3D printers, but it's, yeah. But here's where the real, like the actual human beings sit there and work. So anyway, but yeah, these guys are actually, I mean, they're great to work with, and I'll put a plug for them. How's that? So let's see. Okay, so before I go ahead, I'm going to take a pause and ask if there are any questions at this stage. Sure.
What's the minimum frequency that machine go?
This particular machine?
Yeah.
I'm not sure. Yeah, I don't know. But you can, you know, so the smallest, I don't want to say the smallest, but a very small SMD component that comes to mind is a 0201, right? But they readily can do that.
Okay.
So maybe there are components smaller than that, but that's a pretty small thing, and that machine can do it. Yeah. Yes. Yes. So the schematic, the board, the actual physical design of the board is really not going to look much like the schematic unless you design the schematic with the intention of making the schematic look like the board, which you can do that, but typically you don't. Okay.
Sorry.
This, oh, sorry. So the question was along the lines, let me try to rephrase the question. The person asked about like the schematic design and the PCB physical design are going to look quite different from each other, and I basically said yes. Did that answer your question? Okay, great. All right, so now, are we actually ready to start a design? Maybe. We kind of have a high level of what it takes to do it, but we actually need a few more things. And what we actually need the most are boundaries, okay? So how do we get boundaries for the design process? Well, the first thing we do is we pick the printed circuit board fabrication house that is going to make our board, okay? There are, I don't know, could be more than 10,000 printed circuit board houses on the planet. I don't really know the number, but there are thousands of them. Certainly in the United States, there are thousands of them. Maybe there's 100,000. I don't know. But all of them have similar capabilities, but that doesn't mean that they all have the same capabilities. So if you're going to design a board, the first thing you got to do is figure out what places am I going to source that board from. Maybe pick 2 or 3 just to get a rough idea of what your sandbox is like. I see Gary in the back. So Gary is here. I'm happy he's here because he is our resident Kicad expert. And he's here to save me later if there's a mistake. So I wanted, Gary, you should say hi to everybody. He's the state-of-the-art Kicad guy. Okay. Okay, so figure out what PCB fabrication house you're going to use. What is that going to tell you? That is going to tell you what materials are available for you to use for the substrate of the board, what materials that I'm going to actually go into some detail on, the choices that you're going to have. But it also gives you your design rules. So you will find out from the PCB house how big does your trace need to be. What is the biggest trace you can make? What is the smallest trace you can make? What is the spacing between the traces and so forth? How big can the holes be in the board? Like all these kind of constraints are going to come from the PCB vendor. So you could go out and kind of be like, what's the rule of thumb? That's fine, but the best thing to do is actually just get it straight from the place that's actually going to make the board for you. And if you're making the board in the basement, your own basement, it's up to you to figure out what this is. So, okay. All right, so an exemplar that I want to provide is a place called Advanced PCB. And they just got acquired recently. So some of the charts in here are old, They are using the old website for advanced circuits, but it's basically the same now that it's been acquired by Advanced PCB. And I put their web address there. And the reason I picked Advanced Circuits is that they have a ton of options. Like, you can go from the most complex board to the simplest board in this one place, which is cool. But they also have sort of a lot of information that you can use, like calculators, access to the materials that they offer. So it's a good place to start just to get you exposed to what's out there, okay? So I did have, on that bullet, lots of options, great track record, but then recently, that may not be the case. So but anyway, I still think these guys are good. They're cheap. Okay, so before we get into the nitty-gritty of actually doing a design activity, we all have to be able to sort of speak the language of units that are used in PCB design, okay? So in the United States, which is where we are, we actually still use things that are called mils, which is 1/1000th of an inch. So a lot of times if you go out and talk to a PCB company in the United States, you're going to talk in English units, okay? Obviously they can translate, but the sales guy might talk to you about mils and inches and so forth. So again, a mil is 1/1000th of an inch. It is not a millimeter. A millimeter is a completely different thing, okay? So that's just something I think is useful to know. If you're going to a place in Europe or Asia, then you need to know about microns. So 1 micron is a tiny thing. It's 10 to the minus 6 meters. Human hair is 50 microns, okay? So 1 mil is actually 25.4 microns, FYI. And those are things that you need to kind of have in your mind when you're talking PCBs or going out and working with vendors. And also when you're doing the design activity itself. Okay, so, the final thing before, we've got to figure out how much time I got. Yeah, the final thing sort of before we dive deep into PCB, like the world of what you can get on a PCB, I wanted to make a statement that if you're going to be a PCB designer, you have to also intersect with mechanical engineering. Like we talked about, if you put components too close to each other, then you can't solder it. We talked about thermal issues, like if we have a hot part next to a part that's sensitive to thermal things, that's a mechanical design problem that, PCBs that are complicated, a lot of times might have a mechanical engineer involved in the process, okay? Certainly the iPhone board that I showed, a mechanical engineer probably worked on that as they figured out how to plug it into the iPhone. But for me as I'm an electrical engineer. I'm not a mechanical engineer. I rely heavy on this thing called a caliper. And I think it's a nice thing to have just to check yourself as you're doing a design to see if the numbers on a part data sheet make physical sense, that kind of thing. So I just picked this one. It's kind of a nice one. This is like $200. But you can get El Cheapo ones that probably would serve your purpose. But I think having a device like this has been beneficial to me in my career to sort of help me avoid simple mechanical mistakes as I design boards. Okay, so now we're going to do a deep dive on what options do I have when I go to Advanced Circuits to have my printed circuit board fabricated. Okay. The reason we're talking about this now before we go into the design process is that you have to think, like I talked, we need boundaries on how the design that we're going to do. So this is what's going to give us the boundaries. This is the PCB Fab Shop. They've been acquired. Their website looks different now, but all the stuff is there that I'm going to show you here. Okay, so this table on the right, when you dive into the Advanced Circuits website, goes through all of the materials that are available to you as a PCB designer when you're going to do your board design. So the material that they're referring to here is the dielectric. Okay, so I talked at the beginning, what is a PCB? It is a fiberglass, the most common thing is fiberglass that has copper on the outside that then gets patterned to make the connections, okay? Well, it's not just fiberglass, okay? So the first one at the top, this thing called FR4, that is fiberglass, okay? And that's probably the most common material used on Earth. But there's a whole long list of other things. Basically this whole left column here. Would anybody like to tell me why that might be the case? Why might we need different types of dielectric material in our board?
I mean, there's like a lot of elements you need to get something that's going to withstand that. Probably more.
Yeah. No, I mean, so we got a great answer from the audience. The first was if you're doing RF, you need a low loss material. The second question was related, or the second answer was related to the thermal properties. If you had to use the board in a harsh environment, maybe some of these materials might not work. So that I think that's a great answer. That saves me from talking about it. So, but yeah, so that's exactly it. Now, I'm not going to go into the details of all these, but all of these have a specific purpose that somebody could rely on. And we typically use FR4. We don't worry about halogen-free. So does anybody know why halogen-free is something that would be here? Yes? Exactly right. So the audience mentioned hazardous substances. So the unfortunate thing that happens when FR4 catches on fire is that it releases toxic fumes. Halogens. Halogen-free does not release those fumes. So if you're in a place that cares about releasing poisonous gas when your board catches on fire, you pick halogen-free. So, and it's interesting because in Europe, like, a lot of the, network cables, all this, what do you call it? These things that you're plugging your power into, power strips, like they have to be halogen-free because of that, because they have a really strict rules on what happens when things catch on fire. Okay. All right. So let's kind of look at some other things that they want to tell you about. So here, it's kind of hard to see, but this column is very, very, very important. It's feature size capabilities. So this tells you, as a designer, what size can I make my trace? What size does the space need to be to the next trace? And how wide can it be? And it also tells you there are differences between internal traces and external traces. So if you have a board that's not just 2 layers, let's say it has 4, there are layers that are buried inside of the PCB that have different design rules than the outer layers. So as a designer, if let's say you didn't know this, you completed your design, the inner layers have the wrong rules, you send it off to the fab, they're going to say, oh, you got to redo it. Okay? So it's nice to know this at the beginning so you don't have that issue. Gary, did you ever make that mistake? Gary did make the mistake. So, hang on a second. All right. So another thing that they talk about here are the drill sizes. So the drill sizes are incredibly important. So we haven't talked about it yet, but if you have, let's say, a 2-layer board and you have an electrical connection on the top and you want it to go to the bottom of the board, you somehow have to go through the dielectric material. The simplest way that is done is that they drill a hole through the board and then they plate that hole with copper, making a connection from the top to the bottom. So this is called a via. But the size of those holes are a rule that you have to follow. So that's listed here on this chart. And that can vary depending on how much you pay. So if you want really, really tiny holes, you can pay a lot of money and get laser holes. But if you want a cheap board, then it's just going to be a mechanical drill. So that's something you can dive deeper on. All right. More capabilities. Like these things, we could talk to each of these slides for 1 hour, but we're going to keep it brief. What else do we got here? So here, a machining drill. That's more like, how big can the holes be? Plated through holes. It's kind of what I just discussed. Non-plated holes. So maybe you have a mechanical hole that's not used for an electrical connector. They give you the rules for that. Blind and buried vias. So I told you the simple example that you have a via that goes from the top of the board, drill to the bottom of the board to make the connection. There are more complex vias that actually allow you to do a stair step. So go from one layer to the next, then move over, go to this layer, and do a stair step. So it's not all the way through the board. And this can be useful if you have something incredibly dense or a component that has a lot of connections that needs to be made. Here we are. I talked about micro vias. So if you want really tiny vias, they're laser drilled. And you got to pay more, but it allows you to make something smaller. All right. So these are kind of more mechanical things, which I'll let you read about as you wish. And then finally, I think this is the last slide. Yeah, here we go. On the capabilities, we talked about this at the beginning, solder mask. Guess what? You can get a different color. You don't have to get green. You could get your favorite color. So that's pretty cool. But you got to pay more for that, typically. So Legend is the silk screen. So if you get a board back and you see text written on it that's white, that's the silk screen. There are rules as to what size that can be, like the width and so forth. Go ahead. What's your question?
Why is green?
Yeah, the question from the audience was, why is green the most popular solder mask color? I don't really have the answer. So, I don't know. I'm guessing just like, I don't know. I can't answer. So, maybe come back and tell me next time. How's that? Okay. Really important, very important section here. Surface finish. Does anybody want to tell me what they think surface finish means? Go for it. The audience answered that it has something to do with hot air solder leveling. And in fact, if we look at this list, it's probably there. But what the finish is, I mentioned at the beginning, the copper itself will oxidize immediately if you don't have a solder mask over it. But you have to have a solder mask opening in order to make a solder connection. So what do? You put something on top of the copper that is conductive that you can solder to. So there are many, many options on what you can use for that. The cheapest is what the gentleman over here said, which is hot air solder leveling, which at the end of the day, it will cover the board with solder. So they basically dump solder on the board, they take it to a fan, and they blow the solder off. So at the end, it's not very uniform. Okay, so it's there, it works, but maybe for the design for manufacturability situation, it's not the best. So here, I'll just give you the cheat code. We use something called immersion gold. So basically, that is a plating that is relatively inexpensive. It is relatively flat, and it is gold. So gold does not oxidize really at all, so it actually lasts a long time. If you buy that board, you put it on the shelf for 10 years, you can still come back and solder it. With Hazel, which is hot air solder leveling, those boards, solder alloy itself will tarnish over time and make it hard to solder. So we typically buy electroless nickel, immersion gold, or ENIG plated boards. Okay? Another thing to think about is panel area. Go for it. Okay, the question from the audience wasn't some of the choices, or isn't one of the choices here just bare copper? So maybe somebody wants the bare copper. When they get it back, they'll just eraser it and then solder it. I don't know. There could be a reason. Okay. So now we're into the material science world where we're talking about interface between metals. And the PhD student said, sometimes in really sensitive applications, you might want to have a copper-to-copper bond to make a better connection. So I can't personally speak to that, but it's probably true. Okay. Okay. So panel area. Why does this matter? If you're going to make a board that's like 2 inches by 2 inches and you want to make 10,000 of them, you're going to put them on a panel that has 100 of them so that when you take it to Avcom and they do the assembly, they don't have to handle each little part. They can handle the whole panel, which is a lot easier. So they will tell you, what kind of panels you can make. So stack up, again, we can go forever, but this is how do you actually determine what your multi-layer board looks like and what are you allowed to do? We talked about a 2-layer board. We talked about a 4-layer board. Here, they may talk about the total number of layers. I don't know if I see it here. We probably missed it, but they can probably do at least a 20-layer board at Advanced Circuits, okay? So depending on the number of layers, you'll have different rules for how you can make the stack up. And that's also a function of the final thickness of the board. So we didn't really talk about it, but that dielectric thickness is typically 62 mils, okay? That's the most common thickness. So we talked about green is the most common solder mask. Well, 62 mils is the most common dielectric thickness. Would anybody like to answer or propose a reason to get a thicker dielectric or a thinner dielectric? Okay, like a physical separation. So the answer was maybe you want to keep the layers separated. That could be a valid reason. Any other? Sure. So this is a good answer as well. Let's say you had to actually you needed a board that had some mechanical rigidity. If you made it thicker, it would be more robust. So that's kind of in a nutshell what you said, right? Okay. All right. I think I'm done on this stuff. Do we have any questions about sort of PCB, the space of what can I do on a PCB and how I pick? John, please. Okay, so John's question was, if you pick an option of the board that is more expensive, let's use an example. Like, let's say you wanted a laser drill, but you only wanted one on the whole board. Does that kind of summarize your question? Okay. So the unfortunate answer is typically no. If you put one, they're going to pay, it's going to cost you, right? Because then it has to run in a separate fab, or it has to go to a separate line to do that. Some options maybe not, but some yes. So it's something you'd have to talk to the manufacturer to find out for sure. So the question was, if you had one laser drill, do you then meet the, whatever minimum order to cover 1 million laser drills on the board? Okay. Again, it's kind of maybe, it really depends on the actual thing that you're doing. And, yes, maybe 1 to 100 is good, but if you do 1 to 1,000 is not good. You're going to have that conversation with the PCB manufacturer. Okay, guys.
Did you talk to the ounce, 1 ounce copper is versus half ounce? Did you talk about that?
I did not talk about this. So we have another PhD student in the audience. It's a very important thing to discuss. There's an item called copper weight, okay? So copper weight refers to the thickness of the copper of each copper layer in the board. So that thickness actually has a weight. So the reason they call it copper weight is that they measure it over an area, and a standard copper weight is 1 ounce per square foot. So if you get a thicker copper, so I guess I'll ask the class, why would I want a thicker copper? So the answer was you can now allow higher current. The answer is correct. Then I would ask, what would be bad? Like, why wouldn't we always do this? Why would it be bad to have thick copper? That's one, sure. So the answer was it gets expensive. Do we have anybody else? So the answer was, does it impact the parasitics? Yes, certainly it could. Let's say, for example, you had 2 really tall pieces of copper next to each other. Yes, that would increase the sidewall capacitance. but I'm going to give you guys the answer why it's bad, is that it's actually harder for the PCB house to do the patterning. So if you have really thick copper, it's harder for them to make fine features. Okay? So the features you can make are a function of the copper weight. And I think this was here, maybe I just glossed over it. So, but Mike, thanks for that. Gus, let's have it. Right, so I think it's a great question. So yes, everything that is exposed, once you do one of the plating techniques, so the hot air solder leveling or the ENIG that we talked about, every exposed copper will be covered with that material. So yes, the answer is yes. Now, the PCB vendor, if you wanted to do the thing that the PhD student talked about, that you wanted to have exposed copper and nothing on top, they probably could mask it off for you if you wanted that. But I've never had a reason to attempt that, but I think it's probably possible. Okay. All right. So let's talk about money. What is this going to cost? So, you know, this is one of the things I really liked about Advanced Circuit, and it's still the case. You can get a board for $33. So you do this cute design, and you can send it to them, and they will make you a board for $33, which I think is not too bad. Okay? They have, you know, some other options here, 66. You're like, well, what's the difference between the two? It's 2 layers versus 4 layers. Okay, so you got to pay twice to get more layers. There's a thing called bare bones. Bare bones, I've used a lot of these, and they're really cheap, but they don't have any green solder mask. They're just traces that are covered with hosel, and they're kind of problematic, but they can work if you're really cheap. Okay, so, but here's the rub. If you say, okay, I want my $33 board, right? It's not really $33. You got to buy 3 boards. So you got to pay $100 to get your $33 board, but you get 3 copies of it. Okay? The cool thing here is that at a high level, if you take this deal, you get all the specs dictated to you. So you don't have to call the guy at the company and ask. He's telling you, this is what you're allowed to do. This is your sandbox. Okay? So at a company like Advanced Circuits, it's very simple. You pick this option. You know what rules you have to follow to design your board. Okay? Otherwise, you can call them, and they will, you know, send you a spec document that you have to read through and decipher. This is pretty simple. So if we look here, I can't really see it, but this guy, yeah, I can't see this at all, but it's okay. So they let you do a white silk screen. Somewhere it's going to say green solder mask. It allows you to do 62 mil thick board. What's that line space? I can't see it. So it allows you to do 6 mil space and trace. So we talked earlier about units. These guys are talking in mils. They're not talking in metrics. So, okay. So we've reached the stage that we can actually now design the board, I think. So I've given you guys enough background knowledge that you should be somewhat dangerous and be able to start. So in general, what we're going to talk about today is schematic entry, how to get started. Okay? Next time, we're going to talk about layout, and we're going to talk about manufacturing files. So today, just focused on schematic. And as I talked about at the beginning, what are we gonna consider? I'd like for the exercise to be, we're going to make a thing that's called a shield. So I don't know the reason why they call it a shield, but you know, Arduino is cool. A lot of people make these things called shields, but what they are boards that plug right on top of an Arduino. So, oops, computer is dead. So I was talking before the computer died that we're going to design something called a shield. I don't know how they came up with that name, but it's a cool name because it is basically you're making a board that is going to plug on top of an Arduino. And the Arduino that is used in this student competition and sort of the most ubiquitous one is this called Arduino R3. I have a child that is very young. She has this, I feel like, so let's make something for a board like this. So we're going to make a PCB that's going to plug on top of this. You know, you don't have to do that. Now that you're going to be a PCB designer, you can do whatever the heck you want, but I'm going to kind of use this as the example, okay? Any questions about this? All right. Let me get set up again to what the heck's going on. Okay. All right. So we are now going to begin using Kicad. At this stage, and I will respect everybody's time, we'll be out of here at 8 o'clock. At this stage, I would ask that you all open Kicad, and we're going to make a project. I'm using version 7. I don't know if this is the most recent version, but we are going to make a project. I will do it as well. So File, New Project. I will call mine Shield 2. Okay. And I'm done. So is anybody stuck at this point? Do we have any questions? We've all successfully done this. Okay. All right. So everybody made a project. How many people, if you could please raise your hands, are already experienced with Kicad? Okay. So maybe not as many as I thought. So that's cool. So how this works, once you make a project, you now have access to all the tools you need to design your board, okay? So they are arranged in this panel here. I don't know if it's a panel, but they're arranged here. Starting from the Schematic Editor. So we talked about today, the first thing we're going to do is make the schematic. Below that is something called a symbol editor. What the symbol editor allows you to do is edit and modify symbols that are going to be placed in your schematic. A beautiful thing about Kicad, it has a huge database of already available symbols. And the reason is that it's an open source software. A lot of people use it. A lot of people contribute symbols into their libraries. Also, a lot of commercial companies, for example, Analog Devices, Texas Instruments, they will provide symbol libraries for Kicad. That works in both the schematic space and also in the physical design space. Those in the physical design space, they're called footprints. So we have symbol editor for schematic, footprint editor for the physical design, which is the PCB. For the purposes of this workshop, we're not going to talk about making custom symbols or footprints. That's something you can kind of do on your own. So there's also another key component, which is the PCB editor. That's where you do the actual printed circuit board design. Okay. So below here is something called Gerber Viewer. So this is after you've actually made your printed circuit board drawing in the PCB editor, you're going to generate the files that you're then going to send off to the PCB fab. Those files are in a different format than the native Kicad format. So the reason you have this Gerber Viewer is so you can look at the files that you generated that are going to be sent to the fab, and so that you can see if what you're sending is actually what you want. Okay, because you can actually generate a file incorrectly. So that's there for you to check. Then there's other stuff, image converter. I don't know what it does. I've never used it. Calculator tools. I've seen Gary use this before. I don't know a lot about it. I'm not really going to talk about it, but I think it's useful. You know, you're obviously welcome to play with that if you want. And then other things that I don't know. What I care about, schematic, PCB, Gerbers. That's what I care about because I'm going to design a board. All right, so I have my cheat sheet here. What am I going to do next? So we did this. So we're going to now work on schematic. The most important thing in something that took us a little extra time to get set back up is that I have to have a mouse. I cannot use Kicad unless I have a mouse. It sucks, okay? So I have my mouse right here, okay? So I just wanted to make that point clear. Gary, do you agree with me? Right. It can still be used, but it's a pain. So I also made a note that I want to talk about units. And then I'm going to put some symbols on the board. So I think I can remember that, and I think I'm ready to go. So I'm going to open the schematic editor, and I would ask for folks to follow along. Okay, here we are in the schematic editor. It's fired right up. You know, one thing that I immediately notice about Kicad that is a lot different from other PCB design tools is that it puts on the front page something that always in other programs you got to dig down deep to find. And that is, what is the grid? So the grid is what basically, if you draw a wire, it will snap to that grid. So, you know, in other tools, you have to dive through menus to find the grid. This is just sitting right here on the top left, which is super convenient. Not necessarily in the schematic, but more in the PCB design phase. But I think it's cool about Kicad. The next thing is that the units are here. So you can switch between inches, mils, and millimeters on the fly. Other programs don't allow you to do that. They're actually quite cumbersome. They will actually insert rounding errors and kind of mess up your design. I've had that happen before. But Kicad, I've never encountered it. It's right here on the side. It's super convenient, especially not necessarily in the schematic, but in the PCB design phase. You might get a component that is given to you in the manufacturer that uses metric units, but then on the same board you have a component that's in English units. So you need to swap between the two in order to sort of see if the design is correct, right? So anyway, that's very convenient. I wanted to point that out. Okay, so what we're going to do now is just construct the schematic, a very basic one, just so I can walk through some basic schematic concepts. Here on the right is the place where you grab symbols, which I said these symbols represent components that are eventually going to end up on your actual physical PCB design, but they're a abstract representation of those physical objects. You click on this, and it will open up a list of options that you can choose from. It takes a minute because the database is somewhat large. And so I guess you guys can follow along while I'm doing this. And so here you see the symbol library. So we talked about Arduino. So let's see, does it exist in the library? Let's check. So if I type here ARD, I see on the list Arduino Uno R3. So that is the part that I am going to target. Again, you guys don't have to do it, but I think for the sake of following along, you probably should. So we'll take the Arduino R3. I'm just going to double click it, and it will sort of hang on to my mouse, and then I will left click to drop that into the schematic. And if I zoom in, you see this rectangle with numbers on it. Those numbers represent the pin number. Okay. Now, what do those pin numbers mean? We really don't know yet. Okay. Right now, it's random. I mean, if I just dropped this and didn't know anything about the Arduino, I would have no idea what those pins mean. So we're going to talk about that in a couple of minutes. But it also has labels that talk about what each of these pins are. So D0, D1, D2, up to D13. The Arduino has digital IOs up to 14 of them. Those are there on the left. It has a power supply connection, 3.3 plus 5. It has ground. It has some analog inputs. It has a reset and so forth. So this symbol, you're going to connect electrically to the Arduino. All right. Another part, because the first thing we all did was light up an LED. We're going to also do that here on the board. So we need an LED. So let's just go. And I see conveniently there's an LED symbol. I'm going to grab an LED. I'm going to drop it on the board, and I'm going to rotate it. So I don't remember the hotkey. Gary, what's the hotkey? R. So I'm going to R, and you can see I can just rotate this guy to my heart's content. Okay. If we got an LED, what other kind of component do we need? Resistor, sure. So let's grab a resistor. Okay. Drop this guy in here. And so we've now got an Arduino, we've got an LED, we've got a resistor, and we want to light up the LED. So what are we going to do? Which way does current need to flow in this LED to make it light up? Who's got that? What's that? Okay. What direction does the current have to flow in this LED? So the current flows from the anode to the cathode. So we're gonna rotate this guy like this, and we are going to now make a wire. Just arbitrarily pick one of these pins. Oh, it's kind of weird. Like it doesn't snap that great, but that's okay. Okay, here we go. All right. So I'll kind of pause here, see where everybody's at. How are we doing? Are we good? We got this? Move on. So we now have to connect this LED. We need a current path. Let's choose ground as the node that we're going to make that current go to. So I'm going to go over here, and I can grab a symbol for ground. So let's do that. Take this guy, put it here, make a connection. Okay. Now, who can tell me electrically why this would not work? You're answering too many questions. Go for it. Okay, that was a great answer. Would anybody else like to answer that? Go for it. Say it louder. So we have two answers. Could you repeat yours? Okay, so the first answer was that this is a ground global pin. That is exactly right. I'm going to talk a little bit more about that in a moment. So that's the right answer. Another gentleman over here said there is no current path. So because the Arduino ground is not connected, there's no place for that current to flow back to the Arduino. So we have to connect the grounds on the Arduino. So let's do that. We can, Gary, is it C for copy? What's the copy command? Oh, control, it's like Windows. Okay. Okay. Yeah, it's like Windows. So we do this. We're going to hook this guy up. Ooh, mess. Okay. All right. So now we hooked up an LED to our Arduino. That's great. What we're going to do next, and I'm going to harp on this, is that we talked about the importance of placing components, okay? Right now, we have these components in the schematic, but how do we know what their physical representation is? At this stage, we actually have not determined that at all, okay? So we have to do that first. So I'm going to jump into the PCB Editor, which is here. All right. And this is another thing about Kicad that I really, really love, is the ease of taking stuff from the schematic and then dumping it over to the layout. It is so easy compared to other PCB tools that I've used in my career. So I mean, I just think it's really, really easy. So all you got to do is you push this button right here, which I'm hovering over, okay? And if you read it, it says update PCB with changes made to the schematic. So this is taking the schematic information, dumping it into the PCB. So when I click that button, oh my God, there are errors, okay? Like this is not good, okay? What is it telling me? It is telling me I cannot add D1 because there's no footprint assigned. Kicad does not know what the physical representation of that diode is, okay? So we have to tell it. It's also complaining about the resistor, same thing. So if we go back to the schematic, which is over here, it's really easy to do. You just double click. It opens up the properties, and here you pick the footprint you want. All right. So I feel like they have actually resistors even, which they do somewhere. And I'll pick a surface mount device just because. You can pick whatever one you like. I'll take a 1206 and I'll say OK. And then for the diode, I'll do the same thing. I'll go inside of here. I will click on the footprint. I will, maybe there's an LED. I don't really know, but I'll check. There is an LED. I think I'll go ahead and pick a through-hole LED. And we'll pick a 2-pin guy. This 3 millimeter I know is a pretty standard size, so I'm just going to pick that. Now, I have a lot of knowledge and a lot of background. I just pick these things. I know what they are. I've memorized this. You guys, none of you know any of this at all. How do you find that information? Like, how did I pick the 3 millimeter? How did I know that that's a common part? I have to go to a vendor that sells parts, see what parts are available, read about them, and learn about their mechanical properties, okay? So that's the same thing that we're going to do with the Arduino. It's the same thing we're going to do with the resistor. So all of that, you know, I quickly went through it, but it actually would require real research if you were doing the design yourself. Yes?
Can you quickly show how to get into the PCB editor again? Someone online saying they didn't see where the...
Absolutely, yes, I can do that. If you go back to the project thing, I don't know what it's called, but this is where the project information is. You simply click on the PCB editor. So that you click on this guy and it will open the PCB. Ah, very good. So how do we do the import? We're going to do that again because we edited, we fixed our footprints. So now hopefully the import will actually work. So we're going to do it again. All right. So that button is at the very top of the screen. I don't know if the people online can see it, but I'm kind of hovering there. Okay. So I'm going to click that button again. And I now see no warnings, no errors. We're good to go. All right. So I click Update PCB, which it gives me a list of what it did, a report. Then I close. And now my mouse, without clicking the left mouse button, I have the components in my hand. And I can drop them on the board. And you see, we have this thing called Arduino R3. Okay. We have a resistor and we have an LED. So I will pause and see how you guys are doing.
If anyone needs any help too, we have people that can float around.
Yeah.
Just raise your hand. Yeah.
All right. So we kind of went through what I wanted to talk about. And I realized that we're now out of time, but that's okay because I'm going to talk to you guys about one thing and then I'm going to give you homework. Okay. So the most important thing I want to talk about is that I do not trust these libraries that come to me from an outside person. Even if it comes from TI, even if it comes from Analog Devices, I don't trust what came out of that library, okay? So your job between now and the next time is tell me, is that Arduino R3 correct to plug in to the Arduino itself? Will it work, okay? So how do you figure that out? Well, you've got to go to Arduino. You've got to read about the R3. It's going to tell you the mechanical design. It's going to tell you what pin is what. Like, for example, pin 1 may be here on the top left. What is pin 1, you know, in their documentation? Does that actually correspond? If we go back to Kicad, if I open the PCB itself, it has pins and they're labeled. Number 32, it says number 32 is A1 SCL. Is it actually that? I don't know. I don't trust this at all. If I were designing this board, I would spend an hour checking this part because if I got this wrong, the whole heart of the board is incorrect. I would fabricate the thing, it would come back, and I would have a pin wrong, and it wouldn't work. So that's the key thing to do here before we do anything else. You're going to pick all the parts you want, you're going to put them on the board, and check that they're right before you do anything else. Okay?
You have a question online.
Let's have it.
How do you do the footprint assignment again? Real quick?
Ah, okay, sure. So that is done in the schematic, and you simply either double click the component. So I'm going to left double click. In the table, there is a footprint field. On the right hand side, there's a thing that looks like books on a shelf, perhaps is what this represents. I'm not sure. But you click on this, and then it opens the library manager, and you can pick the parts from the library manager. Okay? All right. So, time for homework. And after this, I just want to kind of close the meeting officially. If you guys want to chat after, that's fine. But in terms of the homework, what I would suggest is that you install Kicad if you haven't already done it. So do that. They have really nice documentation. They have nice tutorials. I would suggest, if you're really interested in doing this, just go to their website, go through one of the getting started guides, and you'll know more than me by the time you come back next week. Okay? So the documentation is great. You'll learn all the cool things that Kicad can do just on your own time. So the next thing I would say, what are you actually going to design? Like you now are working on a board. It's going to plug into an Arduino. Like, what is your idea? Are you going to actually do something? Kind of think about something to make. Make sure that you come up with questions and bring them next time. Happy to answer those, and we have experts in the room. And then the other thing is, like, Gus talked about getting this eval board of the Arduino. I mean, this one that I got for my kid is called the student kit, but it has all kinds of stuff in it. It's got a multimeter. Like, you can do a lot of cool things, and it's like $80. So I would recommend, if you actually want to play with this, it's really accessible from a monetary standpoint. So go ahead. So they do have, so the question was, can you actually simulate inside of the Kicad environment? The answer is they do have a simulation capability. I'm not familiar with it. I've never used it. I've seen it used. There's a lot of information out there how to do it. I haven't done it myself. So, okay. So I think that's going to close the official meeting. Do you guys have to say anything before we lock it down?
No, I think we're good. Thanks everybody for coming. If you have questions for any of us, just stay after and we'll field all of them. And please come back next week for part 2. Thank you.
Okay. Thanks, guys.